has been just about right. This is probably the last algebra session we have for a while, right or not?
Yeah.
Although your geometry class, I would expect them to spend the first week reviewing algebra.
Yeah.
So
Probably.
you're going to have some algebra to start off with. So we may end up with another session on algebra. I don't know. But we should be able to cover everything left here that we haven't covered. Didn't quite get enough time to review it, which I would prefer, but what the heck. Okay. Tell me which of these are exponential equations and tell me which are algebraic equations. First,
The first one is algebraic.
second one,
Algebraic.
third one,
Algebraic.
fourth one.
Exponential.
Very good. Identifying arithmetic and geometric sequences. Have you ever done any of these? Probably not.
Not that I remember, no.
Okay, they're pretty straightforward. Let me give you an arithmetic sequence. And you can tell me why it's arithmetic. What's the next term?
16.
So what makes this an arithmetic sequence?
You're adding 3.
There's a common number that is added to each term. In this case, that is 3. Yeah. It could be 4. In other words, I could have an arithmetic sequence like this. What's the next term?
16.
17. In other words, you have to figure out the common difference. Okay, that's arithmetic, that's arithmetic. Each one of them is a sequence of numbers that are all separated by the same amount. That's what makes an arithmetic sequence. Okay, geometric sequence. What's the next term?
32.
What makes it a geometric sequence?
A common number that you're multiplying by.
Right. In other words, there's a common ratio. And every 2 is twice as big as 1, 4 is twice as big as 2, 8 is twice as big as 4, and so forth. And these also can be sometimes a little strange looking. It's the next term. And what is the common ratio?
Is it 27?
Good. What's the common ratio?
-3.
Perfect. That's all we need to talk about with that. There's some formulas that go with each of those, but it doesn't say learn it, it just says identify it. So I think if I laid out a bunch of sequences, I think you would be able to tell which ones were arithmetic and which ones are geometric. Agreed?
Yeah.
Okay. So let's go on to graphing square root functions. typical square root function is that one. That's the elementary square root function. Tell me how I'm going to graph that. If I don't know what the graph looks like, how am I going to figure it out?
Maybe plug in a number.
Make a table, which is what you're talking about doing.
Yeah.
Okay. And at the top of that table, you have X and Y. Always in that order. And then you need to plug in more than one number. You need to plug in a few numbers. What's a good starting spot?
1.
What's Y when X is 1?
1.
Okay. So that point is on the curve. What's another good number?
4.
Okay. What's Y?
2.
So if I go out approximately 4 and up to 2, that point's on the curve. Let's go back. What's another number for X less than 1?
0.
Okay. What's Y when X is 0?
It's 0.
And that's a very important point. That's the starting point of our curve. Now, can I plug in minus 1 for X?
Yes.
No,
No.
not take the square root of negative numbers. You can take the square root of positive numbers or 0, but only those. So the next one I'm going to plug in is going to be 16, right? I know I could do 9. Let's go back and do 9 since I don't have a lot of room here. What's Y when X is 9?
3.
Okay. Now if I go 9, it's somewhere about there, so that's kind of what I'm looking at. Okay. Now if I connect the dots, and it's not connecting the left one with an arrow, I'm going to put an arrow there because X can go all the way to infinity. In other words, in this direction, X can go as far as I want to the right. And what you end up with is a curve that looks a little bit like this. I haven't really drawn it with quite enough curvature in it, but if you don't know how to graph a function, this is always a way to do it. But you have to know what your allowable domain is. In other words, when I look at that function, I know that I can only use X values that are positive or 0. So my graph is going to start at 0, 0. There's no arrow pointing to the left here. Okay, so the square root function is a little bit of a weird graph. But like I said, now you probably want to memorize this. You don't want to always have to make that table. That table's a lot of work, okay? So it works a lot better if you just memorize what the square root function graph looks like. And that's what it looks like. Okay, and there's really not very many other graphs that look like that. In other words, that's not a parabola, although in reality it's half of one, but I don't want to confuse you with that. Okay, so transformations of functions is once again a big topic, and we've spent like an hour and a half on that. And maybe we'll review it if we have time today, and I think we will. We'll review a few, but let's make sure we do the last couple also. Graphing cube root functions. It's not a square root, but it's a cube root. In other words, it's y equal the cube root of x. Another way to write that would be what?
X to the 1/3.
Good. Now, again, I could make tables, but the real elementary function to memorize, the cube root function is actually, I don't believe that's one of your 10 primary elementary functions. So even though it's nice to know what it looks like, it's not as important as the cube function, which is this, y equal x cubed. Notice the difference, okay? The bottom one is the cube function, and for some reason, in my mind, I always know how to graph that. It looks like that, okay? And notice, what's the domain? What are the allowable x values?
All real numbers.
What's the range?
All real numbers.
Very good. Okay, now the cube root function, it turns out, is just the inverse of the cube function. And the way you get inverses is you start with the dotted line that represents y equal x. That's y equal x, just a line at a 45-degree angle. And then the inverse is the reflection of this. So if I wanted to draw the cube root function, well, if I take the black line and reflect it, you see what I'm doing?
Mm-hmm.
Got to go through that point. So the pink line is the cube root function. And for some reason, I don't know why, my brain, I almost always have to draw the cube function and then reflect it in order to figure out what the cube root function is. Although that's silly now that I think about it, because all I need to do is this. That's the cube root function, which is a little different than the cube function. You really want to know how to do both. In other words, you want to know what the square function, what's y equal x squared look like? It's a call. Actually got a name.
I'm not sure.
A parabola. It's a U. Okay? All quadratics are parabolas. They all look like U's. Some are this kind of U and some are this kind of upside down U, but they're all parabolas. And whenever you have a quadratic, it's a parabola. So the moment you see y equal x squared, that's a quadratic. That's going to turn into a parabola. But when you have something other than the squared, like to the 1/3, then that's not a parabola. That's the cube root function, which is what I've got on there right now. Okay? So we've done that. We've done that. Let's solve radical equations. Very important, actually, this subject, but it's not hard. It's actually fairly easy. We'll start with a real easy one. Solve that for x. That is a radical equation. The definition of a radical equation is it's got a radical sign in it. And it doesn't always have to be the square root radical. It could be a cube root, but the only one you're going to have to worry about is the square root radical for now.
81.
Correct. And how did you do it?
9 times 9.
Well, you squared both sides.
Yeah.
Always remember in algebra that you can do anything you want to one side as long as you do it to both sides. Okay? And when I square the square root of x, notice that I can write the square root of x as x to the 1/2. And then when I square that, I'm applying the rules of exponents. So I'm multiplying the 2 times 1/2, and that gives me x to the 1. And you're right, the right side is whatever number that is. Okay, let's try another. Get a little more complicated here. Give me it line by line. Don't jump just straight to the end. Give me the next row, the next line that I should write.
Would it be the square root of x equals 5?
Remember what you're trying to do when you're solving radical equations is you're trying to get rid of the radical sign.
Okay, then you would square it first, so it'd be x minus 1 equals
Here's what I'm doing. Squaring that side, squaring that side. What's 4 squared?
16.
Okay, and now there's another line. In other words, now I got to finish solving the equation. So x
So then
equals what?
17.
There you go. Now I'm going to change it up just a bit. This time I'm going to do this. Solve that.
So the next line would be the square root of x equals 1.
Yeah, notice that I can't get rid of the radical sign in one step. In order to get rid of the radical sign, I have to isolate. So anything that's not in the radical sign has to be gotten rid of. Then when you finally get down to this step, you can square both sides. What's x equal to?
1.
Okay. Solve that equation. That plus 10 is outside the radical sign.
Okay, so the next line would be 2, the square root of x minus 1 equals 10. And then
It's the next
could
step.
you divide by 2?
Exactly.
Okay, so that would be the square root of x minus 1 equals 5. And then you'd square it, so then it'd be x minus 1 equals 25. And then x equals 26.
Very good. Okay. Just for the heck of it, solve that. This is a radical equation because I'm looking at a radical sign, but it's not a square root sign, it's a cube root.
So you would cube each side. So then it would be x equals 8.
You got it. That's solving radical equations. All right. Let's go back and talk about this topic right there, which I'm not sure how this is ending up at the end of this document because we specifically spent like an hour and a half on transformations, did we not?
Yeah.
Yeah, I thought we did. So I'm going to write some functions, and I want you to tell me what kind of transformation, what the parent function is, and what kind of transformations are going on. Okay. It's the parent function. And I'm going to write the parent function. I don't want to write it as y because it's not really y. Y is this. Y is the transformed function. I want the parent function, so I'll call it f of x.
So f of x equals x squared.
Okay. And what's going on with this function? What's that called? Just tell me how you would change the graph. In other words, you don't really necessarily have to memorize the name. You don't need to know that it's, although in order to do it, it's helpful to memorize what's happening. So what are we doing to this function, x squared?
You would go move up 1.
Okay, that's it. Vertical shift. Okay, now you don't really need the words vertical shift. In other words, if I have, there's my parent function. So if I'm moving it up 1, well, there's the new vertex, and my new function's got to look kind of like that. I don't need to memorize that that's called vertical shift. I just need to know that that means up 1. Okay?
Okay.
However, there are 6 transformations, so in order to talk about them, it's helpful to have words to describe them. And some of them need words. For example, parent function.
X squared.
What's happening? How would you describe this?
It's
In other words, you can't describe it by just saying up or down by some amount or left or right by some amount.
yeah, it's like
So this one has a word you have to use. You have to know the word. Is it first of all vertical or horizontal?
vertical.
Correct. And the reason is that the 2 is outside the function. It's not.
Oh, it's a vertical stretch.
Yeah. In other words,
There.
if I'd have written it like that, then I would say that the 2 is inside the function. And that's a horizontal what?
Horizontal shrink.
Yes. They go opposite. In other words, with vertical stretches, that number has to be greater than 1. If it's a vertical shrink, that number is less than 1. Okay, so this is a vertical shrink, this is a vertical stretch, but when we're talking horizontal, that number greater than 1, that's a vertical shrink, or excuse me, a horizontal shrink, whereas this would be a horizontal stretch if it were inside the function. Okay?
Okay.
I'm going to stick with that function for the moment. What's happening to the elementary function?
Okay,
And
so
work your way from left to right. In other words, don't talk about the +1 first. Let's talk about that first. And then we'll talk about the +1.
so it's horizontal stretch?
When you're adding or subtracting, it's shifts.
Okay.
It's only when you're multiplying or dividing that you get stretches and shrinks.
Okay.
Okay? In this case, we're subtracting. So this is going to be a horizontal because it's inside the function. Shift. The only thing left to specify is which direction.
The left.
Actually, right.
All right, because
It's opposite of this number that I've circled. In other words, the standard is y equals x minus h, where a positive h goes to the right. And in this case, h is positive 2. It's not negative 2. It's positive 2. And positive goes to the right. So, and what else with this function besides now we'll deal with the plus 1. What's the plus 1 do?
it's a vertical shift up
There you go, by
1.
1. In other words, you got to give all the information because that's how you know how to graph it. Vertical shift up by how many? How many is very important. Okay. It's happening to the parent function. Vertical or horizontal? Everything, all 6 transformations, 3 of them are vertical, 3 of them are horizontal.
Vertical.
Correct, because that negative sign is outside the function. So what is it? It's a vertical what?
Vertical translation?
Reflection is the word.
Reflection. Okay.
Okay. Now, what is a vertical reflection? A reflection over which axis? Is it a reflection over the x-axis or the y-axis?
The x-axis.
Yeah, and you have to say that. In other words, your teacher may not accept vertical reflection. That's kind of my own invention because it helps very much to categorize these transformations into 3 vertical and 3 horizontal. And if you think about a reflection over the x-axis, in other words, there's our parent function. If I reflect that over the x-axis, becomes that, and that's a vertical reflection. So it fits with the categorizing that I've come up with. But you would have to give at least that much information on a test. It's a reflection over the x-axis. You wouldn't have to necessarily call it a vertical reflection. A lot of people might not even know what a vertical reflection means, but we do. Now,
It's a horizontal reflection over the y-axis?
huh? And notice what happens if we reflect that over the y-axis. Right?
Mm-hmm.
Well, if we do the algebra here, what's minus x in parentheses squared equal to?
X squared.
The original function. So this negative sign effectively doesn't really do anything. It's not that all negative signs don't do anything. Some do. if we're talking about the cubic function, it looks like this and would be defined as f of x equals x cubed. Now I tell you, well, now I've got y equals minus x in parentheses cubed. What does that minus sign do?
It flips the function.
Still a reflection. Always remember that minus signs in front of the x are reflections.
Okay, so then it's a
vertical or horizontal?
It's horizontal reflection over the y-axis.
Okay, and if I draw that, there's that part. In other words, I reflected that part, and then down here it would look like that. So was that bell on my end or your end?
My end.
I was just wondering. Let's see. So in this case, it does look different. The horizontal reflection, or the reflection over the y-axis, is a different looking function. Now, notice that if I were to write this, what's that?
It's a vertical reflection over the x.
Yeah, notice that if I do a vertical reflection over the x, I get that and that. So with the cubic function, the vertical reflection is identical to the horizontal reflection. And you can see why. If you do the algebra, this top one here, that's equal to minus x cubed. And if you do the bottom one, that's already minus x cubed. So even though one can be depicted as a horizontal reflection and the other as a vertical reflection, they end up being the same function. And they graphically show that also. All right, let's see. Let me give you one that's got a lot of stuff going on. You tell me everything that's going on. And then we'll be done with this. I really think you get this part pretty good. Don't you feel like it?
Yeah.
Might be a little tougher this time.
Okay. So it's a vertical.
Start left or right, okay?
All right, so it's a vertical reflection over the x-axis.
Okay.
And then I don't know what to do with the divided by 2. So.
Okay, that's why I did it. That is the same as that. This is the, I'm sorry, let me just be a little clearer here. Those are equal. These two things. When you're dividing by 2, it's the same as multiplying by 1/2.
Okay.
Okay? So, a multiplier by 1/2 is what?
It's a vertical stretch?
Shrink.
Shrink? Okay.
Okay? Remember that when you're doing vertical stuff, the number has to be greater than 1 for it to be a stretch. If it's between 0 and 1, it's a shrink. So it's a vertical shrink by 2. And what that would look like if I just took the parent function and vertically shrink it by 2, it flattens it out. That's without any of the other stuff going on. In other words,
Okay.
this thing here is y equal x squared. This thing here is y equal x, or we'll do it like I did it, like that. Okay? And this tends to throw people. That's why I gave it to you. Because you want to know that when you're dividing by 2, then it's the same as multiplying by 1/2. Now, let's change it. Speaking of that, let me give you one that is maybe, what's that?
It's a vertical shrink. Wait, no. Vertical stretch by.
In other words, if you were considering the 2 alone, it would be a vertical stretch. But you can't, because then that leaves the 3 hanging as a denominator. So, and then you wouldn't know what to do with the 3. So the better way to deal with this is this. Now what is it?
It's a vertical shrink
By factor of
by factor 3.
2/3.
Okay, so you have to say
That fraction is. Okay?
Oh,
In other words, it wouldn't flatten it in half. In my drawing over here, notice that in the x squared over 2, all the points are about halfway in between the x-axis and the original function. Well, if I shrunk that by a factor of 2/3 only, it might look closer to that. In other words, now every dot should be 2/3 of the distance between there and there. I still haven't drawn it quite right, but I think you understand what I'm saying. Okay. Well, I can't think of, I don't want to get much harder. There are harder transformation problems, but I don't think you're going to be presented with them, certainly not the beginning of geometry. Maybe when you get to Algebra 2. To be honest with you, everything on this sheet is a combination of Algebra 1 and Algebra 2. If you were perfect at everything on this sheet, you could probably pass an Algebra 2 exam.
cool.
Yeah, serious, and you're pretty good. So, in the remaining 20 minutes, let's see if we can do a little review. You feel good about solving equations?
Yeah.
This one, A equals BH, solve it for B. There says solve for H, but I'm saying solve for B. What would B be equal to?
A divided by H.
There you go. How do you identify a function? I'm going to draw some graphs. You tell me which ones are functions and which aren't. I'll draw 4 of them. Starting top left, function or not? Top right, function or not?
No.
Bottom left, function or not?
Yes.
Bottom right.
No.
Very good. In other words, what you're applying is the vertical line test, right? That's
Yeah.
that's how you determine. Is you wherever I run a vertical line, it only passes through one value of y on that top left. But if I run a vertical line there, I pass through two different values of y. That's why it's not a function. Whereas this lower left, I can run a vertical line, only one value. If I try running a vertical line through that vertical line, I get an infinite number of values of y. So that's what you're doing is the vertical line test. Domain.
It's all real numbers except negative numbers.
Well, what's true is that what is inside the radical sign cannot be negative. X can be negative.
It can be -1, but that's it.
Well, okay, so how do we solve for domain here? We start by taking what's inside the radical and saying that it has to be greater than or equal to 0, right?
Mm-hmm.
Now solve that inequality. What does that mean?
X is greater than or equal to -1.
That's the answer. That's the domain. And if you'll notice, that's all x has to be, is greater than or equal to -1. Notice that -1/2 is greater than -1, right? You recognize that?
Yeah.
On a number line, here's a number line, there's -1. -1/2 is right there. In other words, -1/2 is greater than -1. And can I use -1/2? Yeah, because -1/2 plus 1 would be +1/2. And then I'm taking the square root of a positive number. But the secret here is to automatically recognize you're looking at a square root radical and know that the very next step has to be that one. And it doesn't matter how complicated it is. Let's say I did this. Now, let me make that a minus sign. Ooh, boy. Ultra large eraser. So how would you figure out the domain on this? This covers a lot of math steps. In other words, there's a lot you need to know to figure out the domain on this. Start with what?
I would set the x's to 0.
No. Start with this step right there. What are you doing when you make that step?
It would be x squared minus 7x plus 10 is greater than or equal to 0.
That's correct. Now, if I wanted to figure out how to solve that, What do I got to do to this quadratic?
Oh, you would like subtract 10.
Factor it.
Yeah, factor
That's
it.
the answer is factor it.
Got it.
Break that quadratic up into two linear terms. What are those two terms? We'll get a little factoring practice in here also.
X minus 7. Wait, no. It's
What are
it's
the
y.
three steps? I want you to go through each three step and tell me step by step. First step was what?
It's factors. Wait,
No, first step is what? Split the x's up.
okay, split the x's up and then
Second step is what? And this is the most important one. And this is the one that most students screw up the most, is that second step. And the reason is you're trying to do the whole thing in your head all at once, right?
yeah.
You don't want to do it like that. You want to do it step by step. What is the second step?
Um, the signs.
Both of them. Not just one of them, both of them. What are both signs here?
One is subtraction and one is addition.
Actually, the only way I can produce a positive 10 is if both signs are the same.
So two negatives then.
Correct. They could either be negatives or positives. And they are, once you've determined that both signs have to be the same, then you look at the middle term, the minus 7x, that tells you they both have to be negative. Okay? Now, the third step. Specifically, what is the third step?
Factors of 10 that add to 7.
Perfect. What factors of 10 add to 7?
5 and 2.
Okay. Now, you're down to that. Okay? Now, there's a way to solve that. We haven't done the math on it, and certainly don't want to go into it at this late point, and it's not on this list. We don't need to. I gave you this problem just to illustrate to you that when you're trying to figure out domain, no matter how complicated it is, just take it and set it greater than or equal to 0. Okay? And then factor that, take it into two linear terms, and then just trust me that we can come up with a solution here once we get down to this step. It's just that's a little higher algebra than they're getting to at this point. Now, let me give you another one here. Domain. That second step we did on the previous problem, what's this going to look like? X has to be what? Ah, I lost you for a while, didn't I? You back? No. Lost audio. Call.
Okay, you're back?
Now you're back. We lost audio there for a moment.
Yeah.
Okay. I changed the problem just slightly. Y equal 1 over square root of x. What's the domain? What's that critical second step we have to do?
Um,
In fact,
multiply?
let's do this. Let me even make it harder still.
Okay.
Okay. Now, what would normally be the second step?
It would be to write it out, so it would be
Okay, what? Tell me what to write.
1 over...
No. X minus 1. Start with what's inside the radical, always.
Okay, is greater than or equal to a 0.
Okay. Now, here's the kicker. Normally, that's the case when you're looking at a radical sign. Can this be equal to 0?
No.
Because that would cause us to do what?
Divide by 0.
First rule of mathematics, you cannot divide by 0. So this is not greater than or equal to 0. This is just greater than 0. So if the radical sign happens to be in the denominator, like it is here, then instead of writing it has to be greater than or equal to 0, you put greater than 0, and then solve this. What do you get for the domain?
X is greater than 1.
That's it. X has to be greater than 1. It could be 2, 3, 4, 1.5, 1.1, cannot be 1. If X is equal to 1, then I'm going to be dividing by 0. All right, same function. What's the range?
So now what do you do? 1 over...
First thing you have to kind of think about is, can it be 0? In other words, let's examine various y's.
Okay.
In other words, first of all, can it be negative? Can y be negative? Is there any way to make y negative?
No.
No, because the square root of numbers, no matter what x is, the square root of it is going to be a positive number. And I got 1 divided by a positive number. So the very first thing we know is that y has to be positive. Okay?
Okay.
Now, are there any positive numbers? Can it be 0? That's where I was headed. Can y be 0? Is there any value you can think of? And we'll make it simpler here. I'll erase that minus 1.
Wait, no. No, it can't be.
No, because for a fraction to be 0, the numerator has to be able to be 0. And my numerator is 1. So no matter what value I put in for x, I can never make y equal to 0. So the range right off the bat looks like it's at least that big of a restriction, okay?
Okay.
Y is going to have to be greater than 0. We've already decided it can't be negative, can't be 0. And it turns out that, yes, it can be any number above 0. If you wanted y to be 3, I would make x 1/9. Notice that if I had y equals 1 divided by the square root of 1/9, that's equal to 1 divided by 1/3, that's equal to 3. So yeah, I can make y 3. And by that same logic, I could make y anything that's a positive number, including infinity. If I let x get small enough, and then I divide 1 by the square root of that tiny number, then y is going to get extremely large. So y can be any positive number. It just can't be negative numbers. It can't be 0. That's probably the most difficult question you're going to face regarding domain and range, is where there's a radical sign. Okay? And just make sure that if it's in the numerator, make everything inside the radical greater than or equal to 0. If it's in the denominator, make everything inside the radical sign greater than 0. What kind of function is that? Is that linear? Is it quadratic? Is it cubic? Is it square root? Each of those things I said are different types of functions. What kind is this?
Linear?
Yeah, because there's a y to the 1 power and an x to the 1 power. Now, I didn't have to write it like this. If I manipulate this function, I can turn it into those are the same two functions. Okay. The only difference is that to get to the second one, I solved for y. I wanted to get it into y equal mx plus b format. Tell me the slope and the y-intercept.
The slope is 3.
No.
And the y, what?
The slope, here's the standard format that is the most basic format for linear functions. M is the slope, B is the y-intercept.
Okay, so then the slope is -3/4, and the y-intercept is 3.
Yeah, and notice that when it's in slope-intercept format, it's pretty easy to graph, right? I go to the y-intercept to start with at 3, and I put a -3/4 slope in there. Well, a -3/4 slope is about like that. So when you have it in y equal mx plus b format, it's very easy to graph. Okay? However, there's this point here where you got to graph it using intercepts. So instead of going to all of the math to turn it into y equal mx plus b format, let's just graph the two intercepts, the y-intercept and the x-intercept. That'll give me 2 points. Connect the 2 points, I've got the graph. How do I get the x-intercept?
Solve for x.
Well, what is y when I'm solving for the x-intercept? Remember, here's the x-intercept.
Wait.
What's the y? When I'm solving for the x-intercept, like I am here,
Okay.
what's the y value?
4.
No, look on, that's the x value. What's the y value?
3.
0.
Okay.
Right? You see it? Don't look at the function, look at my graph.
Oh, okay.
When my graph is crossing the x-axis, what is the y value? 0, always.
Okay.
You're talking x-intercepts. That, by definition, means the y value is 0. So if I plug in 0 for y, now I can figure out what the x-intercept is real easily. It's 4. Okay? Now, how about the y-intercept?
It's 4.
What's the x value when I'm on the y-intercept?
3.
No.
I'm so confused. I'm sorry.
Well, let's straighten you out before we leave. There's a real simple rule. When you're on the x-intercept, the y value is 0, right? No matter what the function is, doesn't matter if it's linear or not. If I'm on the x-intercept, the y value is 0 by definition.
Okay.
And if I'm on the y-intercept, what's the x value?
0.
Okay, that's what you got to remember. Y-intercepts have x values of 0. X-intercepts have y values of 0. Now tell me y-intercept on this function. What do you have to do?
You have to go.
You have to set x equal to what? On the y-intercept, what's the x value?
0.
Okay, that wipes out that term. When I make x equal to 0, that term disappears. Now I got 4y equal 12. What's y equal to?
3.
There's your x and y intercepts. And that's all I need to graph that line. In other words, if I'm trying to figure out how to graph a linear function, I only need 2 points. Well, I figured out the x-intercept was at 4, 0, and I figured out the y-intercept was at 0, 3. Notice that on the x-intercept, the y value is 0. On the y-intercept, the x value is 0. Draw a straight line through them, and I've just graphed my function. And notice I never had to figure out what slope was. You don't always need slope to graph a linear function. What you need is 2 points. And when you use the intercepts, sometimes, usually the function they give you is very, very easy to figure out the intercepts. Because when you plug in 0 for the other value, it simplifies it tremendously, and boom, it just pops out at you instantly. But the thing you got to remember is that on x-intercepts, y is 0. On y-intercepts, x is 0. All right, Phoebe, I'm not sure. You're back in school on tomorrow, right?
Yeah.
Yeah, you have a full day tomorrow or just part day?
It's just a half day.
Half day? Okay. Well, once you get into geometry, whatever you want to set up is fine. Most people have the most difficult with the first 2 months of geometry, more than the last 3 months. And that's because you start off on geometry learning about proofs, and that tends to throw people a little bit. So by all means, let me help you when you get to that part. You'll probably spend a week going over algebra, which you should be pretty good at. I would think you're going to do okay on an algebra test right now. Okay, so have confidence, don't be worried, and you'll stay in geometry.
Yeah, sounds good.
All right, Phoebe. Enjoy your first day of school tomorrow.
Thank you.
I will talk to you whenever I talk to you.
Sounds good.
Bye-bye.